Hello again and welcome. So this is my final setup for the power supply. If you remember the original setup, I had a white box on top with a couple of fans, and then there was a circuit board hanging off to the side that I was using to control the two power supplies. So that's all been installed inside of this top box now. So there's a power switch. You can see the Ethernet connector off to the side. It just makes the setup a little bit cleaner. Originally the sense wires for this were connected up to the two bus bars, so even though these cables are quite thick compared to what I'm normally testing, the drop across all this becomes pretty significant. So you can see I've added these sense wires. So this is the shunt out of our Centec automotive meter, and we'll be sweeping from 3 amps up to 100 amps with a hold time of 5 seconds. Again, this meter was only rated for a maximum of 10 amps. You see it's starting to discolor. I'm currently putting through about 54 amps, and you can see it's starting to glow red. Looks like it's dissipating roughly 33 watts. So we almost made it to 100 amps, and again, that's the reason that I've added this second power supply, basically doubling the amount of current that we could run through our test samples. This is one of the original shunts that I had made for the UT61E, and to prevent it from overheating, I'm just putting it into this water. So what I'm going to do is sweep this all the way up to 200 amps, and let's just see how it holds up. Again, the meter on the left is looking at the voltage drop. You can see we're looking across the two cables here, and the meter on the right is looking at our high current shunt. Again, this is 50 millivolts is 500 amps, so you can see we're currently putting out 11.2 amps. What I'm going to do is just take it all the way up to 200 amps and let's let it set. See, our copper wire is starting to glow here a little bit. Seems to handle it quite well. So this is nothing more than a piece of copper wire. You can see it's basically 1/10 of an inch. Let's go ahead and check the length of this. You won't get a real accurate measurement. You can see the wire still has some kinks in it. Of course, we're not trying to put a man on the moon right now. Let's just see. I'm going to say we're roughly 3 feet 3 inches. It's probably a little bit longer than that. Again, we started out measuring the diameter of the wire, which was 0.1 inch, and that would be a standard gauge size of 10, which would be 0.1019. And again, the length of the wire was 39 inches. In millimeters, that'd give us a length of 990.6 and a diameter of 2.588. So that gives us a cross-sectional area of 5.26 millimeters squared, and that calculates out to a resistance of 3.1159 milliohms. And that's again assuming that this wire is copper, which I do believe it is. If we look at the weight, this would calculate out to roughly 46.59 grams. So what we can do is just go ahead and measure the weight of this piece, and let's see how close we are. We'll just spool it up into a little ball. Right, again, we're looking for a weight of roughly 46.6 grams. So it looks like our calculations are fine. Before we do anything else, let's just go ahead and wrap this thing up a little bit so it'll make it easier to handle. I'll go ahead and install this into our two clamps. You can see our software is showing that it's dropping a little bit more, but there is going to be a drop across the clamp. So example, if I move this thing even one coil in, you can see we're now at 66 millivolts. So we're at 75. Here we're at 78. So it looks like our software is displaying roughly 3.6 milliohms. And again, we had calculated 3.2. But again, we're not taking into account the resistance drop across our clamps. So I would say again, we're within reason. So I just went back and remeasured everything, and at 78 millivolts a drop across our piece of wire at 23.3 amps, we calculate roughly 3.35 milliohms. And again, the weight of the piece of wire is 46.217 grams. The specific heat of copper is 0.385 joules per gram per degree C. So what that means is if I want to raise 1 gram of copper 1 degree Celsius, it requires 0.385 joules of energy. What we want to know is the heat capacity for our piece of wire. So we're going to multiply our 0.385 times our 46.217. So the heat capacity for our piece of wire is 17.794. So if I apply 100 amps to our 3.35 milliohm piece of wire, that's going to dissipate 33.5 watts. So 1 watt is equal to 1 joule per second. So for 30 seconds at 33.5 watts, we're applying 1.005 kilojoules of energy. So if we take the amount of energy divided by our heat capacity, that's going to give us a 56.5 degrees C rise on our piece of wire. So let's just see if we can measure that. Alright, so I've let our system stabilize for a while. You can see we're up at roughly 27 degrees Celsius. What I'm going to do now is apply our pulse, and we should reach roughly 83 degrees Celsius. You can see we're applying roughly 100 amps through it right now. And again, this will be for roughly 30 seconds. See, the power supply is just turned off. Temperature is continuing to rise slightly. So we only reached 54.6 degrees Celsius, and again we started out at 27, so that gives us a rise of 27.6 degrees. Again, we were looking for a rise of 56.5 degrees. So I can tell you that we've applied at least a kilojoule energy to our piece of wire. So why didn't it get as hot as what we had expected? Well, we're not running this inside of a perfect vacuum chamber. So of course this is going to dissipate a lot of the heat right into the air. Unfortunately, I don't have a vacuum chamber where I can run these kind of wires outside and still maintain a vacuum. But I do have another test that we could try. So this is a Pyrex measuring cup, and you can see I have roughly 500 milliliters of water in here. And then off to my left I have a small heater. So the weight of water is 1 gram per milliliter, and we currently have 500 milliliters of water. The specific heat for water is 4.186 joules per gram per degree C. So the heat capacity for our 500 milliliters is 2093. So the weight of our Pyrex measuring cup is 590 grams. It has a specific heat of 0.750. So that gives us a heat capacity of 442.5. If we add that to our 2093, that gives us a total heat capacity of 2535.5. Of course, there's going to be some air. There would be a temperature gradient across our cup, for example, and of course there's going to be a fair amount of heat that's going to escape into the air. We're not going to take any of that into account. So this piece of nichrome wire that we're going to be using for a heater, Measures roughly 1.08 ohms. We're going to be applying 50 amps through it, so it's going to dissipate roughly 270 watts. I'm going to apply that for 120 seconds, so that equates to 32,400 joules of energy. So if we take our 32.4 kilojoules divided by our heat capacity, which was 2535.5, that should raise the temperature of our water roughly 12.8 degrees Celsius. Alright, so we're all set up. You can see I have a small temperature sensor down inside our water. Currently it's measuring 20.8 degrees Celsius, and we're not putting any current through our wire right now. This is the voltage drop again across it. I'm going to be using this small zip tie to stir our water while we take our measurements. Again, we're looking for roughly a 12.8 degrees C rise. Alright, let's go ahead and start it. Again, this should reach roughly 33.6 degrees. This is going to continue to heat. Or maybe not. So roughly 32.7 I think I saw, which would be roughly 12 degrees Celsius. So what I'm going to do is just give it another pulse. And again, we should see roughly the same temperature increase. So again, we're starting out at roughly 32 degrees. And I'd expect this to reach roughly 44 degrees. Should be slightly less because as the temperature goes up, we're going to lose more heat. There's 44. Oh, she's starting to drop. So again, pretty close. Let's let it settle. Looks like about 42.8. Let's give it one more shot. Let's see if our delta goes down a little bit further. So again, we started out at roughly 12. Our second shot was 10.6. I'm expecting this is going to be a little lower yet. And we're looking for roughly 54 degrees. Looks like about 52.1, 52.2. Well, that's going to conclude my little show and tell for the power supply mods that I've made. I hope you enjoyed them. We'll probably be using this power supply for future testing. I thought I'd give you a little heads up for my next video. These are some of the Flukes that I've tested or I'm currently using. The small one on the left is the Fluke 101. This meter has survived a 13,000 volt, 100 microsecond full width half height pulse. So this meter has never been damaged. There was another forum member that had access to a standard IEC combo generator, and he repeated my tests at 12,000 volts, and his Fluke 101 survived that test just fine as well. To the right of that, I have the Fluke 107. This meter survived 14,000 volts, 100 microseconds. And then I upped it to 15,000 volts at 100 microsecond full width half height, and that finally damaged the meter. Again, this meter was repaired and it works just fine. You've seen it in several videos since then. To the right of that, I have the Fluke 115. This meter was tested all the way up to 12,000 volts with a 50 microsecond full width half height, and like the Fluke 101, it's never been damaged. To the right of that, we have the Fluke 17B+. This meter survived all the way up to 8,000 volts with a 50 microsecond full width half height. It was later damaged at 10,000 volts. I went ahead and repaired it and then I put the rotary switch through a 50,000 cycle life test. And to be clear, that's not one cycle. That's one cycle, 50,000 times. And this meter still works fine, and if you've seen that video, the switch contacts on this look really good. To the right of that, I have the Fluke 87V, and then to the right of that, I have the Fluke 189. I have a friend of mine who purchased an 87V some time ago, and he's a double E by profession, so quite often when I talk to him, he'll bring up this 87V that he bought, and he'll complain about it. What ended up happening in that case is he had an 87.4, and that meter is a lot more like this 189. That meter failed at some point, and he couldn't get it repaired. He thought, well, the 87V, it's just going to be the next, generation of the 87 series. So he gets it, and surprise, surprise, it's a very stripped down meter. He knows that I like this Bryman BM869S quite a bit, and he just bought one of these. It's going to be real interesting to see how he likes it. Now, I've never tested this Fluke 189. Again, this was given to me by a friend of mine, and it belonged to a friend of his that had passed away. Actually, this Fluke 87V also belonged to a friend of mine that had passed away a few years ago. To the far left, we have the Fluke 97, and this is a scope meter, and I bought a couple of these that I plan to use for automotive work out in the trailer. So this has actually been a fairly nice portable scope. I've been pretty happy with it. The very first time that I tested a Fluke 87V, again, to be clear, it was not this exact meter. Basically, what I wanted to do was run it at the same levels that this Fluke 101 had passed at. So I basically applied a 13,000 volt, 100 microsecond full width half height to the meter, and indeed I damaged it. A few people, including myself, were quite surprised that this high-end meter, because this costs about $400 right now, could not survive at the same levels that the Fluke 101 could survive at. Unfortunately, this led to people commenting how the meter didn't fail until it hit 13,000 volts. So I had to keep fielding those comments and basically reminding people that I really didn't know where the meter failed at because I didn't incrementally test it like I had all the other meters. So all I knew is that the meter failed somewhere between 0 and 13,000 volts. So sometime later we repeated the test on an 87V. This was after I had built the new generator that's sitting on the right here. And this was a huge advancement as far as testing these meters, because this allowed me to replicate the test real easily. So then I repeated the test, starting out at 1,000 volts, where I incremented by 500 volts, and unfortunately that meter was damaged at 1.5 kV. So again, that was a big surprise for myself, and I'm sure a few others. One of the comments was, what was the revision of the hardware of the meter that I was looking at? I'm not sure what the revision of that hardware was at the time I ran that last test, but I know it wasn't the most recent. So I've always thought about repeating that test. So some time ago when the channel was getting close to 2,000 followers, I started a poll and I allowed people to pick which meter they wanted to see run. And by far the majority of you wanted to see the 121GW ran. And the second most popular meter was the Gauss and Metrowatt. And the third most popular was to see a repeat of the 87V. Of course, we still can't run the 121GW because it still isn't available. I have ran a Gauss and Metrowatt. I wasn't really impressed with it. It had a lot of issues, but I never did go back and repeat our test using the 87V. So this is what we're going to do. This is a brand new, direct from Fluke, 87V. I just purchased this just for these tests. It was manufactured in December of 2017, so it's just a few months old. So my plan is to take this meter and repeat all the tests that I normally run now, and that's going to include the 50,000 life cycle test on this. I've wanted to repeat that test on another Fluke besides this 17B Plus and just see if another one would perform just as well. And I think with this being Fluke's most popular meter for whatever reason, this is the one I'd like to run. So if you're one of those people that believe a brand new 87V is going to perform well on these tests, this next set of videos is going to be for you. Again, I have no qualms about running this meter to failure. So if you're a Fluke fanboy, I recommend you just don't even watch the video. And as a matter of fact, you probably just want to leave this channel, because I'm going to be putting this meter through all the same tests that I put those Brymans through and every other meter that I've looked at. So if this meter doesn't survive, And you want to complain to somebody? Complain to Fluke. Don't be complaining to me. I'm just going to be repeating the same test that I run on all the meters. And then we're just going to let the data speak for itself. So hopefully this one will actually survive. Again, I don't have any axe to grind with Fluke. I'd at least like to see this meter survive to the levels that this new transient generator would put out. At least it would show that Fluke's made a change to the meter, or maybe that one that I looked at that failed at 1.5 kV was some oddball. But so far when I've repeated these tests, everything basically turns out the same. I've done it a few times now, and basically I end up with the same results. But again, you'd kind of expect that. Most of the companies that I'm buying these meters from will have some type of process control. And of course, the pulses coming out of our transient generator, those are quite uniform. So I think we're just going to have to wait and see. So stay tuned. Hope you enjoyed the video. Till the next meter test. Later.